Okay, it looks like David has posted a bit of an introduction, so I'll take that as my cue to get this rolling. Thanks everyone who's already tuned in, and thanks David for orchestrating. See if I can get this full screen here. It's been to many seminars, and it's a treat to finally be the one on the podium here. Thanks for being here. I'm going to present the work from my Ph.D. thesis, which, as Dave indicated, I defended about a month ago. So I've titled this talk, Investigating the Role of Grain Size in Beach Morphological Change, Insights from a Megatidal Mixed Sand Gravel Beach. And I've also acknowledged my supervisor and co-author, Alec, and really spent a lot of time thinking about this particular beach, and fortunately I feel like we have some insights. We've learned some things. So without further stalling, I will get going. So I'll start things off by showing you some photos from our mixed sand gravel beach study site, and I'll talk a bit more about that in a little bit. So the features in this photo are beach cusps. Cusps are generally described in terms of their horns and bays, the horns in this case being these lighter colored gravelly topographic highs, and the bays being these darker colored sandy depressions, and their wavelength in this case is 5 or 6 meters. Beach cusps also form on sandy beaches, but where they differ from the ones in this photo is in this element of grain size segregation, which here is quite striking in terms of the demarcation between coarse and fine. I will also point out this band of coarse material above the beach cusps, kind of near the high water line here. And this is something I'll refer to later on in the talk. If this talk comes across a bit like a defense presentation, that's because it is. I've made a few changes, but this is largely the same presentation I delivered to the examining committee during my defense a month ago. So I hope it comes across as I hope it will. Here is another photo from the same beach. The patterning in this photo is a bit less striking than in the previous one, but if you look closely, you can still see there's this patchiness in grain size. Again, the lighter colors being the gravels and the darker colors being the sand. So this sort of patchiness or heterogeneity of grain sizes represents a challenge from a predictive perspective where, for example, typical approaches to sediment transport modeling make use of some bulk knowledge of the grain size distribution without provision for heterogeneity in space and time. So in my thesis, I attempted to address an acknowledged deficiency of knowledge of the morphological and sedimentary processes on mixed sand gravel beaches in response to forcing, which are currently fairly limited even on a phenomenological level. So in the way of motivation, here is a simple model of a sandy beach. We've got a swash zone and a berm. And the morphodynamic framework commonly used to conceptualize sand beach dynamics describes a feedback loop between hydrodynamics and morphology, which is facilitated by sediment transport. When applied to a coarse-grained beach, a purely morphodynamic model misses a fundamental component of the system, and that is this element of roughness as determined by the surface grain size distribution. So morpho-sedimentary dynamics was suggested in a 2006 gravel beach review paper by Buscom and Masselink as a framework that would more fully conceptualize dynamics on gravel beaches. And so in this sort of setup, the sedimentology or the texture and by extension the hydraulics or the properties of fluid flow through the bed are intrinsic to this feedback cycle between hydrodynamics and morphology. So also importantly, such a framework implies some relationship between the morphodynamics, the interaction between hydrodynamics and morphology, and the grain size distribution. And there are regions of the beach where morphology and grain size are widely acknowledged to co-evolve, and here I've pointed out two, one of them being the berm and the other being the beach step. The beach step being a discontinuity in slope associated with the bottom of the swash zone, where there's kind of sediment convergence where waves are breaking or where the bore collapses. And one might expect sediment coarsening to occur alongside positive morphological change in places like this. However, quantifying the coevolution of morphology and grain size in a meaningful way is difficult for a number of reasons. One, observations are required with high resolution in space and time, which is particularly challenging in the swash zone. Observation methods in the swash zone, particularly of coarse-grained beaches, must contend with the energetic and potentially damaging shore break. And three, observations of the grain size distribution are inherently noisy, so it's really difficult to observe any sort of signal. So another kind of central goal of my thesis was to address this question with regard to co-evolving morphology and grain size of whether there is a signal to be observed or whether there is only noise. And notably, the only studies to tackle this specifically in the past have done so on pure gravel beaches with limited success. So in broad terms, my objective has been to improve knowledge and understanding of morpho-sedimentary, hydrodynamic, and hydraulic processes on mixed sand gravel beaches, which, in comparison with other types of beaches, namely sand or pure gravel, are fairly poorly understood. And I've done this with an emphasis on field observations. So here's a bit of an outline of the talk. It's separated into three sections. The first treats in situ observations of surface wave dynamics using buried pressure sensors. The second is video observations of beach cusp morphodynamics, and the third treating the coevolution of bed level and mean grain size in the intertidal zone. And these are broken up by experiment. So the first two sections are associated with data from a 2015 experiment, and the third from a 2018 field experiment. And I'll introduce these experiments before going into each of the sections. Our study site is Advocate Beach. So here in this map we've got the map is of the eastern seaboard of North America and Canada. We've got the Bay of Fundy here, Halifax and Boston for reference. And at the head of the Bay of Fundy in this box, that's right about where Advocate Beach is, shown here in the red, by the red rectangle. The beach itself is steep, about a 1 in 10 slope. It's very planar at low tide, and it's got a large tide range of 8 to 12 meters. And it's typically fetch limited owing to its orientation in the bay. The shore break is typically quite energetic, as you can kind of see in this photo I've shown here. Because the slope is steep and the fetch is a bit limited, the waves tend to crash right on the beach with a lot of energy. So there tends to be a lot of emphasis on sediment transport in the swash zone. And here you can see some people for a sense of scale here. So the 2015 experiment was primarily concerned with beach cusp morphodynamics, but we were also interested in observing waves using pressure sensors buried beneath the bed surface, and we had concerns about what the amplitude attenuation and phase shifting effects of the sediment would be on the pressure signal, because we wanted to use the sensors in an array coherent sense. So the timing of arrival of the signal at the sensors was really important. So to investigate this, we buried a vertical array of 4 pressure sensors at the mid-tide level, shown here by the blue dot. Sorry, this is an aerial photo of the study site. I'm going to go back for a sec. And if you look kind of closely, you can see some beach cusps here around the high water line. And the width of the beach is about 100 meters. And then the beach cusp morphodynamics component we investigated using this tower-mounted camera on the beach crest, which looked out seaward over the beach. So we used time exposure type imagery to look at the changing shape of the shoreline and track cusp evolution. And the forcing we characterized using a pressure transducer mounted near the low tide level, shown here by this red dot. And if you can't see what's in the bottom corner here because it's behind my face, this just indicates that the forcing was collected using this pressure sensor. So here's a small schematic of the vertical array of sensors. So they were buried spanning the upper half meter of the sediment column. So questions associated with this first section: what is the vertical structure of pore pressure, amplitude, and phase, and can the pore pressure, amplitude, and phase be predicted using a poroelastic bed response model? So here are some sample data from the 4 sensors. In the vertical axis we've got pressure, and this is with the mean component, the hydrostatic component removed, so we're looking only at the oscillating component of pressure, and time on the horizontal axis. So the blue signal is the pressure observed at bed level, and the purple sensor, or the purple curve, representing data collected by the deepest sensor. So clearly appearing attenuated in amplitude, and can kind of also see some phase lag in time. And our metric for quantifying attenuation was comparing the relative amplitudes of the pressure at bed level versus the amplitude at some depth in the bed. So for a model comparison, we employed the widely used Yamamoto model, which is it's analytic and it treats the sediment medium as a uniformly porous elastic matrix. In this figure, the pressure-amplitude ratio on the left and phase lag on the right for a fixed water depth and frequency are plotted versus sediment depth on the vertical axis, increasing downward. The blue dots here are the observations. So the pressure-amplitude ratio on the left decreases with sediment depth, corresponding with an increase in amplitude attenuation, and similarly on the right, the phase lag increases with sediment depth. So here, by half a meter in the sediment, we've got a phase lag at roughly peak frequency of 0.15 hertz of about 30 degrees, which is substantial. So we were able to estimate or measure all the relevant soil mechanical parameters used in the model, with the exception of the trapped air content, given here by this, given by the saturation, which is given as S. The saturation being the percentage of the pore space, or the fractional volume of the pore space that's occupied by water relative to air. So a model best fit to our observations yielded an estimate of the saturation, and in this case the best fit indicated a trapped air volume of about 10%. The red curve here indicates the model fit assuming full saturation of the bed by water, which is clearly different from our observations in this case. So key findings from this section: large pore pressure phase lags and attenuation were observed, and they were well described by this bed response model, and the use of this model allowed us to attribute the observed properties to a significant component of pore trapped air in the bed. And another important result that I didn't really show here, but came out of the data, was that this pore trapped air appears to be persistent both throughout a tidal cycle and throughout the spring neap cycle, apparently not escaping at high tide versus mid tide or what have you. So the second component of this 2015 experiment was this beach cusp morphodynamics component, which we tackled using, as I said, this tower-mounted camera. So here's the camera in the photo here, and here's Alec risking life and limb, helping set it up. Particular questions associated with this chapter: what are characteristic cusp evolution timescales? We really emphasized this idea of timescale and tried to think hard about what affects it, particularly at this beach. And does the superficial grain size play a role in the evolution of the cusps. And I'm not really going to get into this second point in this talk, but there is some evidence from the data that it does. So the workflow for looking at the morphodynamics involved taking sequences of images captured by the camera. Here's a sample image shown in the top left. So taking sequences of these and differencing them, and then summing those differences to produce composite images like this one in the top right that illuminate regions of the greatest change in pixel intensity. So this image has been rectified, so we're now in XY plan view. And then I used a thresholding approach to estimate the position of the shoreline. So in the presence of beach cusps, I could use these extracted shorelines to infer mean properties of the cusp field, namely the cusp spacing and the cross-shore cusp amplitude, which is just a measure of the vertical relief. So here in this plot, I'm showing many of these extracted shoreline contours, and they've been extracted every 3 minutes, and they're stacked through time from bottom to top. So we have longshore position on the x-axis and time progressing upward on the y-axis. And the reason for this parabolic cutout on the side here is just that the width of the shoreline visible in the frame changed with the stage of the tide. So looking back here, at high tide we see the least amount of shoreline, and as the tide went out, we see more and more shoreline. So that's the reason for this shape here. The orange dots are topographic highs or local maxima that have been extracted in each of the contours. So where there are persistent highs, we have these lines that appear to show up, and those correspond to the positions of cusp horns. So by starting at the bottom and looking towards the top, we can see how as the tide came in, it inundated this pre-existing cusp field, which had a larger spacing, and then around high tide, that cusp field started to branch and shift, and then with early ebb tide, we had the emergence of this new, shorter wavelength cusp field that was quite regular. So of particular note here, the horn adjustment is localized. We see this kind of branching and shifting, and the new horn positions are pretty clearly influenced by the positions of the old ones, which is indicative of a feedback process, and an important result, I think. So here in this plot on the top, we're looking at the very same data I just showed you, only now we're rotated clockwise 90 degrees. So the dots, the colored dots, correspond to the positions of the cusp horns. And the color scale just indicates the shoreline position, so lighter colors being further offshore, and high tide being the darker colors, the time of high tide corresponding to this vertical black bar. So I was able to use the cusp horn positions to come up with time series of mean cusp spacing, which is shown here in the middle plot. And then in the bottom plot, we've got a time series of the cross-shore cusp amplitude. So this is the most interesting thing to look at here, I think, and the thing that allows us to dig into this timescale question a little bit. So with the rising tide nearing high tide, but during flood, we have this period of inundation where the existing cusps get covered by water, and that corresponds to this peak in amplitude. And then around high tide, the amplitude of those existing cusps was reduced to this minimum, and then the new cusp field emerged during this period highlighted in blue. But of particular interest here is this initial period of cusp emergence, where we have this upward tick of the curve here. And whereas the whole formation period lasted about an hour and a half, this period was only 10 or 15 minutes, so quite short. Excuse me. And I've given some incident wave properties here just to indicate that they were more or less constant over this time period. So key findings from this section: in all instances of cusp emergence or cusp formation, the grain size sorting was pronounced. The timescales involved were short. This emergence timescale I just mentioned was on the order of 10 minutes. And this value can be arrived at in a similar way using the rate of change of shoreline position due to tides and the width of the swash zone. So this kind of acts as a constraining timescale imposed by the tides, which also gives us a value of about 10 minutes. And the cusp dynamics are strongly influenced by the tide through the rate of change of the shoreline position, through the position of the shoreline, and through the position of the shoreline relative to any pre-existing morphology. All of these things appearing quite important. So on to the 2018 field experiment. And this one was primarily concerned with the coevolution of bed level and mean grain size, which is something we were becoming more and more interested in as we were looking at this cusp problem. So we looked at this coevolution at two scales, both the beach scale, or the scale of the intertidal zone, and we did this using RTK GPS, or precision GPS surveying, as well as photographic surveying over a fixed grid of points, and also at the scale of the swash zone, using point observations of bed level change using acoustic range sensors and also photographs. So at both scales, we quantified or estimated grain size using a digital grain sizing technique, and the technique specifically was the one from Buscombe 2013. And our ability to carry out this type of study was hinged pretty heavily on our ability to use a digital method. And again, the forcing was characterized by a pressure transducer near the low tide mark. So starting at the beach scale, this was the survey grid that we surveyed after each tide. So each of these yellow dots indicates a station that we both took a position with the RTK and took a photograph. So we had a bed level estimate as well as a grain size estimate after running the photograph through our algorithm. And the grid consisted of these different components. We had one cross-shore transect, two of these long-shore transects, which I've labeled berm and mid-intertidal. And I'll talk more about that in a minute. And then this dense grid of points in the middle. So these two longshore transects, berm and mid-intertidal, most of the data I'll show in the coming slides come from these transects, so take note of those. So for this section, particular questions, or a particular question, are there observable signatures of correlation between bed level and mean grain size change, both in the swash zone and at the scale of the beach? So here's a summary of the beach profile evolution over the course of the experiment, and these are constructed using data from that cross-shore transect. So on the x-axis here we have a tide index. So that's just each single tide index corresponds to a single tide. So we have progression through time from left to right spanning about a week. And then here we have the shape of the beach profile evolving through time, which makes up the shape of this surface. And then superimposed on this surface we have the cumulative change in bed level here on the top. So here this red blob is the position of a high tide berm, and it migrated shoreward throughout the experiment, which is consistent with the migration of the high water line due to the spring neap cycle. And these black triangles correspond to positions of the high water line for each of those given tides. And here at the bottom we have the mean grain size, or the evolution of the mean grain size over the course of the experiment. So brighter yellower colors here correspond to larger grain sizes. So you can kind of see that qualitatively the coarser grains correspond to the position of this high tide berm. And then seaward of that, grain sizes were smaller and perhaps more variable. So here in blue I've pointed out the positions of those berm and mid-intertidal longshore transects, the survey transects I showed in the last a couple slides. So you can see the berm transect for most of the experiment corresponded to the position of this high tide berm, as well as the coarse material associated with that berm, whereas the one I've called mid-intertidal corresponded to, or it was away from the influence of this berm, where the bed elevation was more consistent and we were kind of in these smaller but more variable grain sizes. So here are scatter plots of the change in mean grain size versus the change in bed elevation associated with each of those transects spanning the entire experiment. So here on the left we have data from that berm transect. So we're looking at change in mean grain size and change in bed level from one tide to the next. So at one station the change corresponds to a single point. So interestingly, even though we might, we expect to see a correlation between grain size and elevation at the berm, because we know that's a region where this sort of shows up, we really don't see any signal of that here, or nothing visual at least. I have given a Pearson correlation coefficient with a value of 0.17, and that value is significant, but it's very low. So looking over here at the mid-intertidal transect, we do see a visual signal emerging, and the correlation coefficient is larger. Still not incredibly large, but a signal has clearly emerged here. So here in this new plot on the right, I've plotted correlation coefficients on the x-axis versus the cross-shore position on the y-axis, with shoreward being up. And right here we've got the mean position of the high water line. So the correlation coefficients with 95% confidence interval shown here in blue and yellow correspond to data from the berm and mid-intertidal transects, so corresponding to these data. And here I've shown again this little schematic of the survey layout, just as a reminder. So the data shown in black here are computed using the same, or a very similar analysis to the way we arrived at these data, only we're using each of the 6 transects that make up this dense grid of points here. So what's interesting is that the correlation coefficients pretty clearly increase with distance offshore, or at least with distance away from the high water line and the influence of this coarse berm. Something else that was interesting about this is this result appears to be insensitive to the forcing. So if I carry out this analysis again, but I do it based on some forcing threshold, here I've picked a significant wave height of 0.5 meter. If I compute correlation coefficients on either side of this threshold, I get effectively the same value. And this holds true if I change the threshold, as well as if I use something different like the wave steepness. So this is counterintuitive to me, where I would have expected that, for instance, beach cusps tend to show up under kind of fair weather, lower energy forcing, which yield a striking pattern on the beach surface, and after energetic forcing, things are more disorganized. So where I would expect there to be some relationship with the forcing, it's not showing up. So I'm coming back now to this photo I showed you at the beginning of this kind of beach surface patchiness. And the picture I think we're building here is one of positive spatial correlations between bed level and grain size that arise as a result of positive feedbacks between the texture, the morphology, and the flow in the intertidal zone or in the swash zone. And these features have very short persistence times, so the correlation exists from one tide to the next, but the features are very quickly eradicated with the next flood tide, which has some kind of diffusive effect on the beach surface. So moving on to the swash zone, our point observations at the swash zone, which we collected using, as I said, acoustic bed level sensors which were co-located with cameras. So in each of these units shown on this instrument frame, we've got a pair of range sensors and cameras, and they're looking downward at the bed. So we would set up this frame, which was mobile, could be moved by two people. We'd set it up near the high water line with the incoming tide, and then have it sample as the tide came in and then went back out. So ideally, if we positioned it well, we would have a continuous record of bed level change, at least in between instances of swash run-up, as well as mean grain size, at least when the bed was exposed and not covered by water. So here are some sample data from one of the range sensors. Here in the top plot we have an elevation time series in black, and I've extracted maxima in swash height, which are shown in blue, as well as a bed level signal shown in orange, and this is what we're really interested in here. And in the bottom I've just zoomed in on this rectangle here, and you can see that we are resolving changes in bed level in between instances of run-up, which again is what we're interested in. So some more sample data. Here again on the top we've got an elevation time series, or a swash height time series, and I've included this just to give a sense of the phase of the tide, so high tide being around the middle of the plot. In the middle we've got a bed level time series, so our extracted bed level, and in the bottom a mean grain size time series, and there's a locally weighted regression curve added here just to help guide the eye. And I won't really get into interpreting the implications for morphological change that are happening here, although the morphological context is the formation of a berm at high tide. So here in the bed level time series, a berm formed directly beneath the array, and then this berm migrated shoreward at high tide, so we see this reduction in bed level, and then there was more accretion on the face of the berm as the tide receded. So all I really want to point out here is that qualitatively the mean grain size signal sort of follows the bed level signal, or in both cases there is a pretty clear signal to be observed, and there are kind of finer scale features that we can also look at, like this little bump at the beginning, and there are kind of consistent features that tend to show up in the grain size signal relative to the bed level signal. So I think this is really promising. I'm not digging into it too far right now, but I think that the possibilities for learning things about how things progress in the swash zone, particularly on coarse or mixed grain beaches, is really promising. So key findings from this chapter. We observed this persistent positive correlation between changes in bed level and grain size, and this result was independent of the forcing. So I think this is kind of interesting or telling with regard to previous studies that have tackled this sort of thing, which have all been done on gravel beaches and weren't able to observe a signal. So if you recall, the data I showed from the berm level, despite intuitively being the place where we would expect a signal to emerge, we really didn't see anything. Although in the mid-intertidal zone we did. So it seems that in the mid-intertidal, where the mean grain size is smaller and where things are more variable and perhaps the grain size distribution at the surface is larger, the grain size signal being noisy, a signal is able to emerge there, and one that we can observe where the noise may outweigh any observable signal at the berm level. And this is sort of analogous to a gravel beach, I think, or the circumstances at the berm in my case are maybe representative of circumstances on a pure gravel beach. And also there were these finer scale structures observable in the signals, which I didn't really get into, but again I think have the potential to lead to some interesting insights given further study. So I'll try to bring this all together a little bit. and talk a bit about what I think are the primary implications of these results. So from that first section, it seems that pore trapped air in Advocate Beach is quite important to the dynamics, and moreover, at any tidal beach or any beach that experiences draining of water from it as a result of tides, trapped air should be assumed to be present, and there are important implications for bed stability and the way sediment gets mobilized as a result. And this is also a challenge for using buried sensors, because you have to contend with alteration of the signal in time, in amplitude and phase as a result of this trapped air content. So that means if you're trying to observe waves from beneath the bed surface, you either need an array and some modeling to back out these properties, or probably more easily just port the sensor to the sediment-water interface and just bypass any influence of the sediment. Another important insight, the grain size distribution, I think pretty clearly plays a morphodynamic role, or I think we've presented some, or come up with some pretty compelling evidence that it does so. So in the instance of cusps, where we observed consistent grain size sorting, and we had this concept of emergence timescale, which also there's some evidence that this is sensitive to the grain size distribution, as well as these less coherent self-organized structures, which manifest as this kind of patchiness that I pointed out. Important to note that this is a swash zone result. The data I've come up with are really, I think, are a result of processes in the swash zone, and must be considered a swash zone result. And it looks like, as I kind of alluded to, mixed sand gravel beaches are particularly well suited to observing signals of this kind. So this set of results sort of reminded me of a conversation I had with Paul Hill before a seminar many months ago. I don't know if Paul's here. I'm going to paraphrase what he said, but I hope I do it justice. But we were discussing beach cusps forming as a result of a self-organizing process, and he somewhat skeptically questioned why, if that's the case, if they're forming as a result of a feedback process, why they're not just forming all the time. And I think based on the results, particularly of this last section, I can say with confidence that they are, although it's only a small subset of conditions that lead to this spatially coherent striking cusp structure, like the one I showed at the beginning. But perhaps more of the time, the features that emerge are patchy and less organized, but they're still there, and there are signals to be observed. And I think this is really interesting. And again, like I said, I think there's some great potential to learn more about the phenomenology of sediment transport in the swash zone, and the role grain size plays in, for example, the evolution of the berm, or the evolution of the beach step, or what have you. With that, I'll give credit where credit's due, to my co-author and supervisor, Alec, to Richard Cheel for helping with all of the field work that I presented. He was really instrumental, so to speak. To the Hay Lab, of course, and to everyone who had a hand in past field work. And I also want to take the opportunity to thank the Department of Oceanography, since I didn't really get a chance to during my defense. I've been involved in this department for the majority of my 20s, and I'm grateful for it. It was a great time, and thanks to everyone who makes the department what it is. It's a wonderful thing and a wonderful place to spend time. So thanks again, and I will take questions if I can figure out how to answer them. It's very strange speaking to a computer without any feedback. I feel like I'm talking to myself. Okay, so question from Dave Greenberg. What was the time resolution of the buried pressure sensors? Did the high water swash line vary with 1. the high water, the low high water of the day? 2. Did it vary with the spring neap cycle? Or 3. The last storm? Are there multiple lines giving some sort of history? Give me a moment with that. Take that in. The sensor resolution was 6 hertz. 50 hertz. 50 hertz downsampled to 25, I think, was what we landed on, which proved to be ample, I think. The high water line, or the position of the swash zone, definitely did vary with, the tide, but also on a quite substantially at times on a tide-to-tide basis, with the changes due to the spring neap cycle, as well as smaller changes throughout that cycle. And yes, the storminess also greatly impacted the width and position of the swash zone. Are there multiple lines giving some sort of history? Well, this is, I guess I would say that this is something that was kind of tricky to contend with, and it's come up a lot. The fact that we're trying to look at processes, particularly with the cusp stuff, for example, that are centered around, that rely on some mean position of a shoreline, but that shoreline is changing through time and from tide to tide. So you have spatial coordinates that define that you're working within. If you're saying whatever 0 is your shoreline position or your mean shoreline position, but also you have this change in shoreline position through time. So it's a big complicator, having to work with frames of reference that are changing in time. But we tried to mitigate that as much as possible, or learn from it, I suppose. I might be dancing around your questions here, because if you'd like something other than that, perhaps you could clarify. Thanks, Dave. Okay, Rachel has asked if I can comment on the beach shape above and below the waterline. The measured the cusp profile is defined at the water's edge, which is true. And we see the cusps after the water has receded, but we can't see what's underwater at high tide. So how does a longshore variation in grain size due to cusps affect unobserved or lack of relationship between wave height and grain size at intertidal height? So for the first part, you're right. There's not much we can do about seeing, or at least using the methods that I've used about seeing what's going on below the water's surface. There is some wisdom that has been gained about that, mostly from modeling efforts or from sand beach efforts, which people have maybe tackled using some acoustic instruments as well. And on sand beaches, you sometimes see kind of an inverse pattern to the cusp pattern. So at the base of the cusp bays underwater, you would see kind of a mound where presumably the sediment being pulled offshore with some sort of jet gets deposited in a bit of a mound, where there's something of a depression seaward of the horn. Whether something like that is occurring at our beach, I don't think I'm really able to say. Although oftentimes what is striking is the texture rather than the morphology. So whether or not there are undulations, I would expect there to be some kind of change in the texturing, but there's really not a great way to look at it. And as to the second part of your question, let me just read that again. How does a longshore variation in grain size due to cusps affect the observed relationship or lack of relationship between wave height and grain size at intertidal height? Not entirely sure I understand your question, Rachel. Variation in grain size due to cusps affect the relationship between wave height and grain size. I'm not sure that's... If I understand correctly, I'm not sure that's a level of detail that we observed, or from a signal that was observed. There was, I didn't really show this, but there was very consistently a very strong relationship between grain size in a mean sense, averaged over the whole beach, and wave height, or any measure of wave energy. And this was strikingly predictable. So when the energy was high, the beach surface sediments were fine, and when the conditions were more fair weather, we consistently observed coarsening. So alongshore variations, for example, as a result of the presence of cusps, I don't think we were able to look at that beyond things happening in a beach mean sense. So I hope that answers your question. Okay, looks like we're leaving it at that. So thanks everyone again for tuning in.